Welcome back, my friends. This is Aryan sir from entrances.co.in. A wonderful question on thermodynamics relating first law and specific heats and degrees of freedom. So, what exactly are the things needed here? The first law of thermodynamics, and specific heats and degrees of freedom. Well, I would like to go into a bit of detail relating these things so that we can solve this question super fast at the end of the discussion. Very important thing. I'm not here intending to give you a shortcut tricky approach. No way. Let's go into the details of the subject. Let's understand it. The first law of thermodynamics says that Q, the heat supplied to a system, is equal to U plus W. U is the internal energy of the system. Any change in internal energy is because of the amount of heat supplied. Heat is always supplied on the basis of a change in temperature. That means the heat that is being supplied, if that is equal to Q, that Q is equal to N CV delta T, where N is equal to the number of moles. If there is a change in temperature of the system, then you can say either heat is liberated or heat is absorbed. Heat, energy, cannot be stored into a system. Many a times we hear things like heat contained in a body. Sorry, wrong statement. It's a wrong statement. Absolutely wrong. Heat cannot be stored. Heat cannot be contained in a body, in a system. Heat can be exchanged. Heat is like an energy in exchange. You give up heat, you cool down. Your temperature reduces. You absorb heat, you warm up. Your temperature rises. So, as long as there is a change in temperature, there is a transaction of heat, and heat flows from a hotter body to a lower body. I mean, a cooler body. So, there is a NCV delta T relation. Here the CV is calculated. The basic concept of the specific heat is that specific heat of a material with a given condition that the volume of that matter does not change. Let's say we boil water in an enclosed container. So it's a fixed volume situation, enclosed situation, like in a pressure cooker. The volume is fixed and water is boiling. That process of heating up of the water, boiling of the water is happening at a constant volume. So specific heat at constant volume process is equal to amount of heat absorbed or released by the body upon number of moles into change in temperature. This is a basic concept. So therefore, when we look at the first law, this being the first law of the thermodynamics, and is extremely simple, I hope all of you must be knowing this. In this first law, delta U is the change in internal energy. The change in internal energy U is basically a function of temperature. It is not at all a function of the path in which the state changes. It's just a function of the state. It's a function of the temperature. It's a function of the state in which that system exists. So it is equal to, like, let's say for a diatomic gas, if we take a diatomic gas, then it is 5 by 2 RT. RT as at a temperature T, this is the internal energy. So that means delta U, that is change in internal energy, will be equal to 5 by 2 R into delta T. Why 5 by 2? Because degrees of freedom for a diatomic material, degrees of freedom for a diatomic material, degree of freedom is 5. Now what exactly is degree of freedom? The degree of freedom is the number of independent free movements that a molecule can make. Like for example, if you just have a tennis ball, monoatomic. If you just have a tennis ball as an atom or a molecule, it is a monoatomic object, monoatomic, you can say atom or molecule. It is like a tennis ball, It can have only 3 different types of independent or free motions or movements in which significant amount of energy can be consumed, like moving along a direction x or along y or along z. So 3 degrees of freedom. Now if you ask that what happens if it, let's say, rotates about its center of mass about any axis, then let's say this is the x-axis and it rotates about this x-axis. The problem is the mass radius distribution is so small of an atom that it does not consume much of half capital I omega square, capital I being moment of inertia. It does not consume significantly any much of rotational kinetic energy. So you need to be cautious about which types of motions or movements carry significant amount of energy or energy consumption happens. So it happens along a motion if it is moving along x-axis, or it moves along y, or it moves along z. So degrees of freedom for a monoatomic molecule would be 3. Now in case of a diatomic, how exactly does a diatomic molecule or an atom look like? It is almost always of the shape of a two masses M1 and M2, two atoms connected by a rod, a rigid rod. Now if it is a rigid rod connection, if the structure of the molecule is such that its shape, geometry does not undergo any change, then you can call it as a rigid diatomic molecule. And let's say these are the two atoms whose masses are M1 and M2 and separated by a distance d. And let's assume this as a rigid rod. Compared to this is given another case, compared to a rigid molecule is given a case where it can have vibrational modes. That means if we take the case of a vibrational mode or having vibrational mode in a diatomic molecule, then let's say we consider a diatomic molecule with vibrating modes. Now dear friends, here is a extremely nice realistic example. This mass, say M1, is one of the atoms. This mass, say M2, is another atom. These are the masses. And you know what? They are connected using a electron sharing structure which resembles that of a spring, a mechanical spring, which can extend, which can compress. So this spring can have a two-way motion. Either it can expand or even it can compress and like that. And how is this possible? Because the center of mass of the masses or of the two atoms remains at its place, but the two atoms can have a relative motion with respect to each other because of the electrostatic forces of attraction, maybe, or maybe because of the packaging in a high density, packaging of the atoms in a very high density in a crystal lattice. There are several possibilities. While heating up, the matter expands. The atoms or molecules consume higher space than when they are in a colder state. So this can be modeled as a case of a diatomic molecule with vibrating modes. Now, what are the degrees of freedom? Now let me first explain the degrees of freedom. Now this particular atom, whose classification is of rigid type, can move along x-axis, can move along y-axis, can move along z-axis, also can have, like let's say it is aligned along x-axis, then while it is spinning about the x-axis as an axis itself does not consume much of an energy, but it can have a rotation about this particular axis. It can have a rotation which is, let's say, the y-axis. It can also have a rotation about the z-axis. Imagine this. If it rotates about the z-axis, then there is a significant amount of energy consumable because there is a large mass radius distribution. There is a significant moment of inertia involved over here. So in all, 1, 2, 3 as linear translational motions and 1 and 2 as rotational motions. Total degrees of freedom in this case is equal to 5. So I will write here degree of freedom, and let's call it equal to F1 is equal to 5 in case of a rigid diatomic molecule. Compared to this, when you come to a diatomic molecule with vibrating modes, yes, of course, all the above degrees of freedom remain intact without any change. It can move along x-axis, it can move along y, it can also move along z. It can also rotate about the y-axis, it can also rotate about the z-axis, similar to something which we saw earlier. Let me just repeat once more. And like this, apart from these 5 degrees of freedom, it can also have a motion some way like this, that let's say the atom is rotating about the z-axis like this, as well as it is undergoing oscillating motion. The atoms are oscillating about their mean position and are also rotating. Very similar to how an electron orbits around a nucleus in standing waves. Let me show you. If this is the nucleus, an electron orbits around the nucleus maintaining standing waves like this as per de Broglie theorem. Let me draw it properly, just a moment. And like this, maybe it is not exact, or yeah, it may be better. Like this, about the mean path. And this is how the wave nature is demonstrated by an electron while orbiting around the nucleus. Very much similar to that, an oscillating motion of the individual atoms about their mean position is very much a possibility. That means they can oscillate about their mean positions along with rotation. So now don't you think there are several possibilities like this? While orbiting around the y-axis, this can happen. While orbiting around the z-axis, this can happen. This can happen means oscillations can accompany rotational motions. Oscillations can accompany translatory motions. Even while moving along x-axis, it can keep oscillating like this. It can have a springy or vibrating mode like this. So if I say the degrees of freedom has, let's say, degrees of freedom as equal to F2. As equal to F2. Don't you think this F2 is going to be greater than 5? In any case, this is going to be greater than 5. And this is where the classification matters, whether it is having vibrational mode or is it a rigid molecule. Now, how does it relate to internal energy? This is how it relates to internal energy, as you can see. The delta U in this case, because of this 5, it is equal to, let me write down, 5 by 2. For rigid molecules, it is equal to 5 by 2. But for a vibrating molecule, diatomic vibrating molecule, this delta U value, will be equal to F, let me call this F equal to F2, F by 2. Half RT is the amount of energy consumed per mole per degree of freedom as per equipartition of energy theorem or analysis or research. Then if this is F by 2 into R delta T, now you can use this. Now you can use this for the first law. In case if you are considering constant volume process, W is equal to 0 because work done in expansion is 0 because no expansion is happening because you are considering constant volume process. So therefore, the heat that has been supplied to a system in a constant volume process is this. And now let me equate the things. So it is equal to Q is equal to delta U leads you to where? Q equal to delta U leads you to N CV. Delta T is equal to, let's say, 5 by 2 R delta T. And of course, this is for N moles. So I should have into N here. So N into delta T, if they cancel, CV becomes equal to 5 by 2 capital R for rigid type of diatomic molecules. This is a basic calculation. As we know that Cp is equal to Cv plus capital R, so that is equal to 7 by 2 capital R, again for rigid molecules, and therefore definitely gamma 1 value, gamma 1 is equal to, therefore gamma 1, that is Cp by Cv, is equal to 7 by 5, is equal to 1.4. This is usual. This is very common knowledge which we all carry, which we all have. This is the unusual thing in this question which attracted my attention, and hopefully it must be looking challenging to you all as well. Like this is particularly a very nice area where they have asked a question. Now suppose if I go for the vibrating mode, then what would I do? Then what would I do is something that I would learn from here. You learn from here. This 5 is the degree of freedom measure which they had used. So if I now go for, let's say, gamma 2 calculation or Cp by Cv for a vibrating mode, then let's say I call it Cv. Let me call it Cv2 for a vibrating mode molecule. Let's say for a vibrating mode molecule, Cv2 is equal to, should be equal to how much? If you see this calculation, Cv2 should be equal to 5 by R, F by 2 into R. This should be equal to F by 2 into R. It will be having the same logic. NCV delta T will be equal to F by 2 R delta T into N. Cancelling everything, you can have Cv2 is equal to F by 2 R. Instead of 5, you will have F. Now F is greater than 5. Please keep this in mind. Cp2 is equal to Cv2 plus R, has to be. So therefore this is going to be F by 2 plus 1 into R. And therefore gamma 2 calculation, which is going to be Cp2 by Cv2, is equal to F by 2 plus 1 upon F by 2. Where does it lead you? Where does it take you? It takes you to a calculation where you can say 1 plus 2 by F. See this, 1 plus 2 by F. And what was exactly the calculation for gamma 1? It was 1 plus 2 by 5. If you see this, this is 1 plus 2 by 5, and where the 5 is the degree of freedom in the denominator. So this was 7 by 5, 1.4. This 5 has been replaced by F, a higher value. That means 2 by 5 was 0.4. 2 by F will be less than 0.4. F is greater than 5. So therefore 2 by F is lesser. So that means this is going to be definitely less than gamma 1 as a calculation. And therefore this is going to be the correct answer of this question. Thank you for your patience.